Alright, for this video we're going to be looking at biasing our MOSFET. And when I talk about MOSFETs now, we can assume it's an E-MOSFET and an N-channel device. Alright, that's the assumption we're going to make. Because they're the most common now, that's what we're working with. So let's start with our drain curves again. So our E-MOSFET, I have a set of curves that do something like this, where we have VDS along the bottom and we have ID along the top here. Now there's two regions that you can operate realistically in if you've actually got this device on. There's actually three, which we're going to talk about. But realistically, we have the Ohmic region, which is all of this region here, and we have the active region, which is all of this region through here. Alright, so two regions. In the active region, the FET is equivalent to a current source, while in the ohmic region, the FET is equivalent to a resistor. In fact, it's a voltage controlled resistor. Alright, so those are the two operating regions. Active, this guy, he is normally for amplification. Okay, you're trying to make an amplifier. We're not interested in that within this course. Alright, I'm going to skip amplifiers using MOSFETs. Alright, instead we're going to be focusing on the ohmic region, and this is what we use for switching, which is generally what you're going to be doing with a FET. So we're interested in making this look like an resistor, this FET. And so realistically the model that we can use is something like this. Remember, we're using an N-channel E-MOSFET, VDD, that goes to ground, voltage on the gate, that becomes VGS, drain resistance, and this is our FET, VGS across here. This is approximately equivalent to, remember, voltage controlled resistor, VDD, resistor, ground, and this guy can be controlled by VGS. So the resistance here can be changed by changing VGS. So we now have two resistances in this circuit, RD and RDS, and this is nothing more than a voltage divider, which we all learned about in first year. So there's nothing complicated about this circuit. In fact, all I've done within this circuit is actually bias it in the ohmic region already. Alright, so the biasing resistors, all I've required actually is this guy here, and normally that's your load. So in terms of having to add a whole lot of complicated resistors everywhere, this is actually it. There's not a lot much more to it. The only thing we need to be careful of is the value of VGS. Alright, depending on the value of VGS changes this resistance here, which is going to move our bias point. So let's see how this looks. Alright, this is the circuit that we're going to be working from now. Generally, RD is your load, whatever you're switching. So if we draw our drain curves again, which look something like that, we can now draw our load line on this. So VDS versus ID. The current flowing through the drain will be there. Now, the maximum voltage that could exist across VDS, which is across FET, voltage drain to source, will be if there is no current flow. If there's no current flow, there's no voltage drop across that resistor, therefore this device is effectively off, and the maximum voltage we'd have would be this point here, or the maximum voltage in the circuit, VDD. Correspondingly, the maximum current that can flow, so max voltage equals ID is equal to 0, therefore VDS equals VDD, and the maximum current that can flow, we'll change that to a comma, is when ID, let's say RDS, this resistance here, is equal to 0, and therefore ID is only equal to VDD over RD. This voltage divided by that resistance, assuming that this guy goes to 0. So RDS equals 0, the only resistance in this circuit, series circuit, is RD. Alright, and that gives us a point up here, for example, VDD over RD. And this actually has a name. Okay, this is known as ID sat. Alright, so the definition, ID sat equals VDD over RD. Or the maximum current that can flow given that load or drain resistor there. And what we do is we can draw a line, I'll try my best, between those 2 points. Right, that line is fixed based on that load resistance and the voltage applied to the circuit, VDD. Okay, so based on those couple of points, normally they're fixed in the circuit. These curves are fixed by the device. Right, so we've chosen a FET and we get given these curves. We can't do anything about those curves. Right, so these are fixed by the circuit that we've designed. What we can then do, the freedom what we have left is in VGS. So we are now free to change VDS. Now we remember that our ohmic region is here and our active or saturation region is on this side. So if we want to be in the ohmic region, which is preferable, and I'm going to tell you why shortly, we want to make sure our VGS, remembering this might be, let's say 2, 4, 6, 8 volts. Each of these blue lines is a VGS value. As we increase VGS, we come up this line from 2 volts to 4 volts to 6 volts. And so you see by increasing VGS, we move from saturation region to the ohmic region. And correspondingly, therefore, VDS goes down. Alright, as you see, as we follow this line along, VDS, our quiescent point, let's say if we end up with VGS equals 6, our VDS has actually gone down quite a lot. Now that's good. We don't want a high VDS. P FET, the power dissipated by the FET, is equal to VDS times ID. Now normally, we want to switch a lot of current, but we don't want a large volt drop across that device. So as we come up this line, what we're actually doing is changing the volt drop here. So this voltage here, VDS, the voltage across this resistor here. And the way we're doing that is by changing the resistance. Right? As the resistance goes down, the voltage drop across it goes down. Okay, VDS equals RDS times ID. Right? ID's, let's say, is fixed, therefore the only thing we're changing is RDS. Alright, so we are actually reducing the power normally as we come up this way, dissipation across the device. So we're making it a more efficient switch, which is what we want. Alright, so by increasing VGS, we're coming up this way and we move ourselves into the ohmic region. In fact, generally, I would suggest we'd want our Q point about here. The only way we can do that is by changing VDD or RD. Alright, the load is fixed, the voltage in the circuit is fixed, then we need to get ourselves another FET, one where the ohmic region is a little bit more flexible for us. Alright, so ohmic region biasing, as I've done here. This is the load. Often that's a fixed load you can't do anything about. Often the voltage is fixed as per you've got 12 volts in your circuit. That's what you're going to have to use. The things that you can adjust is VGS, and by doing that we work our way up along this load line, because each of these is an increase in VGS, and we eventually put our ohmic point as far as we can this way. The further this way we get, the less VDS is, and therefore the less the power dissipation is across the FET, and the more current we're actually switching as we're going this way. Obviously there's a limit to VGS based on what's practical in the circuit. If it doesn't work, then you need to choose a different FET with a different set of drain curves that will solve the problem for you. So things to remember: the FET can be modelled as a resistance, RDS, this guy here. And because of that, it becomes a voltage divider, which is very, very simple to solve, and the whole reason this exists is because within the ohmic region, the FET, due to its construction, is a voltage controlled resistor. As we change the voltage, this resistance is changing, and therefore the current and voltage drop across it changes as well. Alright,